Okay, so the first thing, let's see, yeah. Okay, so the first thing that we had to do was the drivers noticed with the original Swerve code that it was very difficult to make fine adjustments. What was happening, and it took us a little bit to figure out what was going on, was so they'll move the robot a little bit in one direction to try and line up with something, and as they release their hands from the joystick, the position for the wheel azimuths would change. Now, the wheel speed would be at 0, so theoretically, the robot really shouldn't be moving. However, nothing's perfect, and as the azimuth modules spin, the robot will actually shift an inch or two left or right, or in some or some other direction, just as the different wheels move a little bit at different speeds, or one grips the carpet a little bit more than the other one. And so what was happening was, as the wheels would go back to their home position when the drivers released their joystick, the robot would shift. And so as you're trying to make these really fine lineups, every time you got close and let go of the joystick, all of a sudden your robot would move off to one side. And so given that problem, does anyone have any thoughts on what solutions we could apply to mitigate that? And some of you may remember it because a number of you worked on it at different times. Juliana, do you remember? This was one of the ones that you and Lindsay were working on for a bit.
I don't really remember. Did we just, I don't really remember.
Okay, so that's not a problem. So anyone else have any thoughts? If we wanted to keep the wheels from shifting the robot when we let go of the joystick?
Maybe you measure how much is coming from the joystick and whether it's constant or something, and then you tell it no.
Okay, so that's pretty close to what happened. Basically what we did was we checked to see if the joystick was going from outside of the deadband to inside the deadband. And if that was happening, we remembered we looked backwards in time to remember what the joystick, the commanded azimuth angle was prior. And we continued applying that angle even as the joystick entered the dead zone, the deadband. And so we did that so does that solution make sense? So we're remembering an older command to carry us through into the deadband so the wheel stays in the same orientation. Does that make sense? Okay, so the way that was done was inside of this latch angle block. And all we have is a Boolean coming in that says whether or not the joystick is in the deadband. And if I recall, let's see, it is in the deadband if we're in the deadband for both the rotation joystick and the translation joystick. So both of those have to be in that deadband for us to be considered in the deadband. And we have a rising edge trigger. And so if we're not in the deadband, so we're driving the robot and we enter the deadband, we get a true signal briefly. And when we get that true signal, what we're going to do is take a memorized, let me start the other way. If we don't have that true signal, so if we're driving, so if we haven't entered the deadband, we're going, excuse me, okay, I see. So ignore that section for a second. The last select block is choosing whether or not we're using the remembered goal angle or the current goal angle. So if we are not at all in the deadband, then we are using the typical goal angle that we're getting off the joystick. And then if we are in the deadband, we're going to be ignoring the command from the joystick and using some memorized value. That memorization occurs as we get that true pulse off the rising edge trigger as we enter the deadband. So as we enter the deadband, we store in memory the previous command, and that is what's going to get passed through this second select block into the outputted goal angle. Now, the reason that we've got 2 feedback nodes instead of just 1 is we found that if we record the command of the joystick as it passes through the deadband, that's usually a little bit too late. So that's the joystick's already made a significant change from what its previous azimuth angle was. So it's like at the tail end of the driver releasing the stick. And we solved that really easily by just adding another feedback node. So we remember 2 loop cycles back. So we remember the command, not at the time that we pass through the deadband, but at the time one loop cycle previous to us passing through the deadband. Is there any questions about that? Okay. If we'd wanted to look back more than 2 loop cycles, we could do that. Sort of one way is to just keep stacking feedback nodes. So you'd have, if you want to look back 3 loop cycles, you'd have to have 3 feedback nodes. That starts to get a little bit cumbersome. Something that I learned recently is that you can actually set a single feedback node to look backwards in time a certain amount. So the way you do that, if I can remember here, is you right-click on it, and then let's see. If I can remember. Where is it? Okay, you go to Appearance, and you go to Z Transform Delay Node. And now, right now, this -1 is indicating that we're looking 1 loop cycle in the past. If we right-click on this again, I've only done this once. I only found this out recently. Properties, there we go, Properties. And then Configuration, you can increase that delay. So now we are looking backwards. We're looking at the value from 4 loop cycles previously. Does anyone have any questions about how to modify that feedback node? Okay. So yeah, so this would allowed us to replace the 2 feedback nodes with a single one of these Z transforms. Yeah, Amelie says she also didn't know how to do this. Yeah, I only discovered it the other day. I was messing around with something, and I stumbled across that setting. So okay. Let's see. Okay, so the next thing wasn't really to solve a problem specifically, but it's easier to explain this first and then talk about solving the problem later. So these large case structures out here are handling our different drive modes. This year we did have 3, although one of them is not fully implemented. So we have the normal drive mode, which is actually perhaps the most complicated, so we'll come back to that one last. We also have an auto-targeting on the feeder station, which was never fully finished, although if you press the button, it will work. The one I want to talk about is auto-targeting on the target itself, which is here. So those were set by a variety of different buttons, which I'm trying to even remember what they all were. I believe basically auto-targeting for the goal turns on when the driver holds down the shoot button. And so that's all being decided out here. And there are special cases to make sure we're in the proper drive mode when we're climbing and when we're in autonomous, et cetera. So that's where what's going on here is just deciding what drive mode we're in. So if we're in the target control mode, what we'll see is that the left X and left Y axes, so the translation axes on the joystick, they go straight through without modification. So in other words, the target control completely ignores the translation aspect of the robot. What we do see is that targeting control does modify the rotation axis for the joystick, rotation axis for the robot. And so what we've got going on is we have a PID loop, and the goal that we're trying to get to is typically 0. So ignore the line that's coming in for right now. We just have imagine that we're trying to get down to a goal of 0. And the reason our goal is 0 is just like with the other rotations, like on the rotation on the Azimuth module, our process variable is an angle. And in this case, we've converted it into an angular distance. So this fused heading to target error is the angular distance, either positive or negative, based off of the combination of the robot's estimated location and the line light data if you actually see the target. So it's a combination of both of those, and it's, we're 20 degrees away positive, or negative 30 degrees away. It's a number like that. And we're trying to drive that distance, that angular distance, down to 0 with the PID algorithm. The output of that PID algorithm is basically the joystick command. So it's replacing the rotation joystick for the driver. It's taking over control of the rotation joystick for the driver. Does anyone have any questions about the idea of having the PID loop substitute for one of the joystick axes? Okay. Let's see. So one of the things that we did run into is that auto-targeting is not perfect by any means. And so the drivers felt that they needed some way to be able to override auto-targeting if they needed to. And we, of course, had override set up, but we wouldn't necessarily want to turn off all of the auto-targeting options when we do that. And so what we gave them was the ability to adjust the auto-targeting. And essentially, the way that works is if we've got some angular error and we're trying to get down to a 0 degree goal, our goal is to get down to a 0 degree error. What we can do is we can modify the goal a little bit. So if we have a goal of 0 degrees, that's us pointed, if we succeed at hitting our goal of 0 degrees, that's us pointed at exactly where the robot thinks the target is. If we have a goal of +5 degrees, that would mean that we are pointed 5 degrees clockwise relative to the goal. In other words, we're still positive 5 degrees away from where the robot thinks the goal is. And so by changing that goal off of 0, we're able to actually change the robot's orientation without having to do some weird mix between the robot power, without having to do some weird mix between the joystick power and the PID power. This allows us to have a lot more stable fusion between what the robot's trying to do and what the driver's trying to do compared to last year. So last year we had, again, a manual fudge factor for the driver and a PID loop when we were targeting on the rocket, but we were combining the power output. So we would combine the PID power output with the driver power output, and sort of weird things would happen then if the driver accelerated very quickly or changed velocity, that the PID wouldn't be able to compensate properly. Here we have a lot more stable of a behavior because we never turn off the PID. We only work with the PID. All we do is change what the PID is doing a little bit. And basically we mapped the rotation joystick to that goal. So if the rotation joystick goes from -1 to 1, we now multiply it by this fudge factor, in this case 5. So if the driver presses all the way to one side of the rotation joystick, we're going to modify our goal by +5 degrees. or if they go all the way to the other side, we'll modify the goal by -5 degrees. And so by using the joystick, they can fine-tune the robot's angular position. And then if we want to give them more control, we would increase the manual fudge factor. If we want to give them less control, we would decrease the manual fudge factor. Does that make sense? Are there any questions with the fudge factor? Okay. The other thing that we have going on here is we have this override profile line. This, honestly, we didn't think through this particularly well, so it's kind of messy and not great. But essentially, we don't want, so PID algorithms assume what we call linear responses. They assume that if they increase the power by a factor of 2, like if they double the power, the robot's speed should double. And when we're in the driver profile, that's not what happens, right? We've added that, you know, that x squared curve or the x cubed curve to change their sensitivity. And so if we have the PID algorithm go through the joystick scaling, all of a sudden, we've got a deadband to deal with, which PIDs also don't enjoy. And we've got that very nonlinear curve that is changing the power outputs in a way that, again, the PID is not built to handle. And so when we're running PID on these axes, we actually have to disable the joystick scaling so that we don't get instabilities in the PID algorithm. Are there any questions about disabling the joystick scalings in this case? Okay. Are there any questions at all about auto-targeting controlling the drive base? Okay. So now that we've looked at how the PID algorithm can interface with the joysticks, let's go back to the normal drive mode, and we'll see that we've got a PID. Okay, we'll go back to the normal drive mode. So the problem that we ran into on the full field was that because the robot's weight is not directly over the center of the robot, and not all the wheels are inflated to exactly the same level, and not all the swerve modules are completely identical, as the drivers would drive at higher velocities across long distances, the robot would start to rotate about its center axis. So even if all they're doing is strafing left, right, or forward, back, the robot would actually drift in this angular orientation. Now, from a controllability standpoint, this is okay because we still have an IMU. We're still in field-oriented control, so even if the robot's drifting, the forward on the joystick still means down the field, and left, right still mean left, right. So the robot's still going where it needs to go, but as you try and line up for a shot, or as we found, as you try and line up to go underneath the trench, underneath the control panel, having that robot in the angle makes things a lot more difficult. In particular, with the control panel, the robot, when it's sort of a diamond shape, really doesn't fit under the control panel. So that was starting to be a real problem. And so we wanted to look at a way to keep the robot straight without the drivers having to have so much drive practice that they would be able to intuitively, ride the rotation joystick the whole time. That's how a lot of teams solve it, is the drivers have a lot of drive time and they manually control the rotation at all times. We didn't think we were going to get that kind of drive time, so we went ahead and tried to make a software solution. Does anyone have any thoughts on how we might approach the problem of keeping the robot from drifting?
Do we set the robot heading to like 0 and then have it like PID to correct it?
Can you say it one more time? Sorry, I missed part of it.
If we set the robot heading to a degree that we want it to be, like if we're going straight, then it could PID to correct for the drift.
Yeah, so that's fundamentally correct. So instead of setting a goal angle based off of the target position, we could set the goal angle based off of what direction we want to be pointed at. which I'll get to in a second. And we can use the same PID algorithm to make sure that we stay to ride the rotation joystick, so we stay pointed at that angle even as we're strafing around the field. So as we talk about having the robot control its angular rotation automatically, what are some of the things that we might have to think about and be careful about while we're having it do that? What do you guys think? How do we get an automatic rotation control to play nicely with a driver who may also want to rotate the robot or not rotate the robot? Ethan, what do you think?
So the drift that it's detecting has to do with the deadband, right? Like it thinks that the joystick's moving, but it's not really.
Not quite. So this is actually, so even if the joysticks were perfect, we'd still get this drift. So the drift is the result of, even if the wheel modules are pointed perfectly on the robot, different weight imbalances will cause essentially different velocity vectors on each of the wheels. And so the robot's going to actually start to rotate around its center axis or a different center, even if all of the commands to it are perfect, telling it just to strafe.
Well, then if a driver is going in one direction, like you would be out of the trench, right? And you're kind of holding a straight heading, so there shouldn't be too much difference in how you're moving the joysticks. You could have some kind of limit set to if the joystick moves, number of to like a significant distance, so like we're trying to turn or something, then it would allow the drivers to move. But in a kind of limited window or very small adjustments, it would take over.
Yeah, so I mean, that's exactly right. So the first step of this is that we're only going to give the robot control of the rotation axis if the driver is not, if the rotation joystick on the driver's side is not inside the deadband. I think I may have used tweak double negative there. So if the driver's hand is not on the rotation joystick, then the robot has control or the ability to control the robot's orientation. If their hand is on the rotation joystick, then we immediately cede full rotation control back to the driver. Does that part make sense? Okay. So Alex asks, would there be hysteresis for that? Yes, that's a really good question. Yes, and no, there is a way. There is something that serves as a hysteresis for this, and we'll talk about that in a second. That's a good question. What else? What other problems could you guys foresee? Even if we have this, so at this point we've got we'll only give it control when the driver's not trying to turn. What other problems do you think you could run into with this balance between the automated rotation and manual rotation?
We might not want it to try to maintain its heading when we're going at slow speeds, so we should only do this at high velocities.
So why would we maybe not want to do it at slow speeds?
Because the driver might still be trying to line up, but take their hand off the joystick for a minute.
Yeah, so that's correct. So fundamentally, the problem we ran into is that the rotation lock is good, but it's not great at its job. And so, it's a PID loop, so there's going to be oscillations involved whenever we enter the rotation lock. And then on top of that, there's going to be some error, right? It's never going to be exactly perfect. And a lot of that error is actually driven by the fact that our loop cycles in the robot aren't quite fast enough. So by the time that the robot has remembered the orientation, by the time the robot has decided that, yes, the driver is no longer on the joystick, the robot has already drifted a little bit, but the value that it remembers of what heading it should have been at is now different from that drifted position. And so as it enters that rotation lock, it's going to try and go back to that remembered orientation. Not the orientation is right at that second. There's always some lag in how the sensors are reading the orientation and how we're reading the values of the joystick, et cetera. And I was sort of surprised that it was enough to matter, but it looks like, you know, maybe it's probably 100 milliseconds or something like that. The robot rotates so quickly that 100 milliseconds or so delay is enough for there to be that error. And so, yeah, you're right. If you're trying to line up and you take your hand off the joystick, and it's going to go in, if it went immediately into the rotation lock, the robot's going to start to twitch. It's not going to sit still there. The other sort of related thing to that is a little bit on the safety side of things. If the robot isn't in the cart, or even if it's not in the cart, if it's on the ground, and the IMU starts to drift, and no one's touching the joystick, the robot will start to spin to try and correct its angle. Or if the robot is on the cart and someone bumps the cart, if the robot's enabled, all of a sudden the wheels are going to start to rotate. The modules are going to move, the wheels are going to start to spin. Theoretically, the robot could be disabled and someone spins the cart or moves the robot on the ground, and as soon as you re-enable the robot will try and spin to come back to that orientation that it was at when it got disabled. And so what you're seeing over here with all of these true-false lines coming into this gigantic OR is basically a set of all of the situations where we don't want it to do a rotation lock, either for safety reasons or to allow us to do fine-tuning or to give the driver full control. Before I go through each one of those different situations, does anyone have any questions about that concept or those problems? Okay, so the first situation in which we don't want to be using rotation control is, let's see, if we are going at lower speeds. So so exactly to Juliana's point about when we're going at low speeds, A, we're not drifting a whole bunch to begin with, and B, it's probably because we're trying to line up with something. So we need to not go into rotation lock at low speeds. The way that was set was again, not by velocity off the wheels, which perhaps may have been would be more robust, but by the amount of power that's being applied from the strafe joystick. So looking to see if the strafe joystick was past 20% of its total magnitude. We can look at doing things based off the wheel velocity later on. Let's see, the next line here is whether or not the rotation joystick is out of its deadband. So if the rotation joystick is at all out of its deadband, then we're not going to do a rotation lock because that implies that the driver is actually trying to rotate the robot. The next one is, when the robot is in robot-oriented mode, the rotation lock is turned off. I do not recall off the top of my head if that was just a safety feature or if the algorithm does not work in robot-oriented control. I have to think some more about that one. The next one is we don't want it to try and be rotation locking while the driver is recalibrating the gyroscope, the IMU. So they did have the option to come up against a wall and reset the IMU if it ever started to drift. We don't want to try and be doing the rotation lock right as the IMU is getting reset. Not only that'd be annoying to try and hold the robot, to fight the robot and keep it straight. But also, if the IMU is off by a lot and all of a sudden you reset it, the memory and the PID kind of freaks out, right? All of a sudden, you're very far away from your goal because the remembered goal was based off of a wrong IMU angle, and so the robot will kind of freak out and start spinning. For a very similar reason to that, we also don't do rotation locking when we push the position on the robot, because again, as part of that push operation, you're also updating the IMU angle too, so you're resetting that there, and we don't want it to freak out in that situation. The next one is making sure that rotation lock only happens during teleop. There could be some advantages. So we don't want the rotation lock to be on during disabled. That way, if we come out of disabled mode, we aren't in rotational lock. So there is that section. Now the question arises, do we want rotational lock to be on during autonomous? Does anyone have any thoughts about rotation lock being on during autonomous or not? What would be the advantages and disadvantages? Alex, what do you think?
It could be good so that we like hit our goals and stuff. We don't like go all over the place. But then it could be bad if like you lock onto the wrong goal. Because you can't
Okay.
like
No, go ahead and finish your sentence, Alex.
you can't adjust.
Yeah, so that's one issue is there's not a human at the controls to notice that something's going wrong and correct for it. So that's certainly true. There's a bit of a coding problem with it in the sense that we never really got around to seeing how. So when we're following the path, we already have essentially a rotational lock because we always have a goal robot angle that we're supposed to be at. So when we're following the path, we've sort of already got this, and then we never got around to being able to test the interaction between the goal orientation changing, the goal orientation changing while we're following how the orientation PID and the path follower would interact with the rotation lock PID, right? They could end up fighting each other. And we never really messed around with how to safely switch off between the two of them. So theoretically, we would need something where if we weren't in the path follower, we would use the rotation lock, like if we were doing just the drive straight X or drive straight Y command, we would have the rotation lock, but we need to be able to switch it off cleanly when we're in the path following operation and sort of switch back and forth cleanly. I believe there was also a problem with how the rotation lock handled the autonomous test mode. So when the robot is on the cart and can't correct for its angle if the IMU starts to drift and we're testing autonomous modes, I believe there were some problems there too. I think all of those could be solved, and it would certainly improve the efficacy of some of the simpler autonomous commands, but it requires some more integrated coding to actually handle those special cases. And then I think the last one here, okay, and the last one here is don't go into auto targeting mode if you've just changed your drive mode, or sorry, don't go into rotation lock if you've just changed your drive mode. And that had to do with giving enough time to reset the PID algorithm. If you're switching back and forth between auto targeting and normal driving. So you could imagine a scenario where, for whatever reason, the driver takes their hand off of the trigger for just a second. You'll all of a sudden jump from the auto targeting PID into the rotation lock PID, and there could be some weird interactions there. Are there any questions about those different situations where we don't want rotation lock to be turned on? Okay, so now we should go back to Alex's comment about should there be hysteresis? And the answer is yes. Theoretically, we should be able to be pretty good without a hysteresis in this case, assuming that we were very careful about how we handled the memory inside the PID. So the derivative the points we're referring to with the derivative, and then also the memory that's included in the integral. We should be able to switch back and forth pretty quickly without too many problems. What we found, and quite frankly, I never had enough time to go through and debug it all the way, was that as we go through these different situations where we don't want the rotation lock, even if we had to keep the rotation lock turned off for a certain amount of time in order to re-enter it stably. And my guess is that the fundamental reason for that is buried in some of the parallel loops that we're running and some lag in how the sensors are updating and how the joystick values are updating, et cetera. Because the robot's orientation is so dependent upon all these different values, any sort of latency seems to cause some problems. And I think those could be handled cleanly without a delay, but we never really got around to it. We just didn't have time. And so the fix that ended up happening was to add a hysteresis. So basically, if any of these cases are true, so if any of these situations occur where we don't want the rotation lock to happen, we start a timer, and we only allow the rotation lock to come back in once the time on the timer has exceeded, in this case, 500 milliseconds. So every time one of these events occurs, we reset the timer back to 0, and we wait another 500 milliseconds before we allow the rotation lock to re-engage. Now, one of the disadvantages of this is we aren't recording the robot's angle at the time that the events occurred. We're recording the robot's angle at the time that we're allowed to start doing the rotation lock. And so the robot will drift a little bit in those first 500 milliseconds. After the first 500 milliseconds, it will stay locked to that drifted position and won't drift anymore. One option that we could consider is either removing some of the problems so that we can reduce the delay down to a lower number, like say 100 milliseconds, so you want to drift it as far. Or another option is remember the robot's orientation at the time that the last event occurred. And then when the robot's allowed to do orientation locking, it will have a goal of that remembered angle, and it will have drifted, but now it will try and correct and go back to the original, the last commanded orientation from the driver. That could be beneficial. It could also cause problems just because the robot could start to wiggle more. So there's going to be a lot of tuning involved as we look to improve this going down the road. Are there any questions or thoughts or comments about the rotation lock? Particularly any ideas on improvements, or if Adam or Ethan or Familia's on here want to comment on what it felt like to drive with the rotation lock? Ethan and Adam, did you, I don't remember if Ethan got to drive with it all, or Adam, what were your thoughts on driving with the rotation lock? How did it handle? You never really got a whole bunch of time to dig into it. I wish it would tell me if like Adam was typing or something, but it does not.
I didn't get to mess around with it a lot, but with the drift was pretty, when we were messing with my controls, I remember when we were tuning, when you did not have any like kind of drift adjust, it was, I mean, well, yeah, like, what's the terminology for it?
Say that one more time. Sorry, I was reading Adam's comment.
Without any autocorrect, it was pretty hard to drive, for sure.
So Adam's comment was he thinks it was definitely helpful, but could still be better with more tuning. And yeah, I agree. I think we saw that there was certainly oscillations. It kind of kicked in at maybe not, it would not necessarily kick in at the time that the driver would expect it to kick in. And so that can also make it kind of weird to control. Ethan sent into the whole chat there. So are there any other questions about the rotation lock before we go on? And Ethan's turning bright red right now, which is amusing. Okay, so
why is it autocorrected to that? How does it know that word? Ethan. It's terrible.
You know. So the next thing I want to talk about is how do we handle when the drive modules fail, and what are the different things that we need to consider? So does someone, maybe Alex, want to talk about what kinds of things might cause one of the drive modules to fail?
Yes. Okay. So my least favorite is when it gets unplugged from the stupid Robo-Rio, which was dumb. Second favorite is
Sorry,
when,
can you specify what gets unplugged?
oh, the encoder cables going to the Robo-Rio breakout board, they're like PWM wires and they like to come off, and it was stupid and I was not very happy about it. The second one is just like when the power goes out kind of, and the like modules are like not getting the signal from the encoders because the power went out, but then it just resets itself. So you just have to clear the error and then it's good. And then when you kill an encoder, it also does not have a fun time.
Okay. So I'm trying to think if there's any other ones. And I guess if the motor got destroyed, that would also take out the Swerve module. Or if like the Spark speed controller went out, that would also take out the module. So let's say that we'll start with the easier one first, perhaps. Let's say that the drive wheel on the Swerve module goes out. So that would be we lose power to the spark or lose power to the drive motor. What are, I guess the first one would be, what kinds of things would that be a problem for the driver? I guess the answer is yes. What kind of things can we do to make it less of a problem for the driver if the drive wheel goes out? That one's kind of, I guess maybe that was the tougher one because we didn't really have a solution for it. So, you know, you still want that wheel to be pointing in the correct direction as all the other wheels, so you can maintain some of your vectoring ability. You would ideally want to put the drive wheel in coast so that it can slide, but we drove with the drive wheels. Hang on. Let me see if we did drive with the drive wheels in coast or not. Let me confirm that. I think, yeah, we did have the drivetrain in coast, I'm pretty sure. I have to go back to the begin VI to check. Or sorry, in break. Let me now have to check. Okay, so the drive wheels were in brake. So ideally, if we were to detect a problem with one of the drive wheels, we would put it in coast so that it wouldn't cause so much resistance to the whole robot. The other thing that we would ideally do is remove the calculation in the, so when we're calculating the robot's position, we're using the encoders from all 4 Swerve modules. And when those Swerve modules go down, we would ideally also want to drop out that module from that pose calculation because it's no longer correct. Like we're getting a bad encoder value. The problem that we ran into was we didn't really have a robust way to detect when. Is that true? I'm looking at this and I've got module faults coming in. Okay, yeah. We didn't have a really robust way to detect when a drive motor failed on the Swerve modules. I did mess around at the very beginning with looking at the amount of current that we were drawing versus the amount of power that we were applying. But the current reading off of the PDP board was so noisy and inconsistent that there wasn't like a really reliable way to detect that, hey, we're applying a lot of power, but we're not getting any, we're not drawing any current on the motor. Now, we were able to detect when the Azimuth module failed, the Azimuth motor failed. Does anyone remember how we detected when the Azimuth module failed? Do you remember how we're detecting when the Azimuth module fails? Azimuth motor fails? I can't tell if she's there or not. How about you, Alex? I'll jump back to you.
Did we check to see if the encoder was moving and like if we told it to move, it didn't move?
Yeah, basically. So I think the technical check was on if we've been away from our goal for a very long time. So if we're trying to move the Azimuth module to a different goal azimuth angle and it's unable to get to that location or read that it's gotten to that location, then we identify that something's wrong with that module. Does anyone want to comment on, so say we've detected the failure of one of the Azimuth motors or the Azimuth encoder. What kinds of things could we do in order to improve the driver's ability to continue controlling the robot, even in the situation where one of the Azimuth modules is dead? Juliana, what do you think? What kinds of approaches could we take to reduce the impact that missing an Azimuth motor would have on the driver's experience?
I'm not entirely sure.
Okay. How about Adam? You know, you think about it, right? What we're trying to do is you've got the Swerve module, and all of a sudden it's lost the ability to control its angle. What kinds of physical things might we do to that Swerve module to make it easier to drive on? And I'll wait for him to type. Okay, you can switch it to coast mode. So yeah, that's one of the things we definitely did. So by switching the Azimuth motor from brake to coast, there will be less, if we then also apply 0 power to the Azimuth motor, it'll be a little bit easier for it to rotate freely. So as the robot sort of limps around dragging the dead module behind it, the wheel should start to at least partially align with the robot's direction of travel, almost like a caster wheel. Now, it won't quite do that super reliably because the azimuth, the axis of rotation for the azimuth is actually straight down the center line of the wheel, which is what we want to be controllable, but it doesn't quite have the caster wheel property of slewing around to line up with the direction of travel. So you can see that here in see the azimuth control. If we detect a module fault, we just go ahead and switch the mode on the azimuth motor from brake to coast. And the other thing that we do is we stop applying power to the azimuth motor. So at least the motor's not just like constantly spinning around. So by default, if you unplug the encoder wire from the module and don't do anything to it, it's going to continue to rotate around and around and around and around, trying to get to a goal that it can never see that it gets to. So we also cut power to the azimuth motor. Does anyone have any other thoughts on things that we can do when an azimuth motor fails? So since the azimuth motor is no longer holding the position, there's certainly no guarantee that the azimuth motor, that wheel module is pointing in the correct direction. And so we probably should also not be applying power to the drive motor. So when we detect a module fault, we're also cutting power to the drive motors, to the drive motor on that wheel module, so that if it's pointed in a weird direction, we're not also like trying to drag the robot sideways. So we're down to just the 3 modules that are working, and then sort of a completely dead module that it kind of sucks, but still but at least it's not pointing off in random directions and trying to drive the robot in random directions. And then the last thing that we do is, because we can detect the azimuth failure here, we can go ahead and remove that module from the calculations that are determining where the robot is located on the field. So we can remove all the encoder information from that wheel module in our bigger calculation about what the robot's location is on the field at any given time. Are there any questions with those concepts before I go through the code that's handling that? Okay, so all the actuator faults right now are being handled inside of get low priority sensor values. As I've thought more about this, I think some of the false Swerve module failures, Swerve module failures that we were getting, where it would detect a Swerve module failure that didn't actually occur, may be the result of the fairly long delay time on the low priority sensors. And so I think going forward, we should be looking at moving the Swerve module failure detection into a higher priority loop that isn't waiting so long. But right now, they're inside the low priority sensors and inside this actuator faults block. Inside the actuator faults block, we're doing a number of things. We're checking all of the motor temperatures, for example. We're also checking the shooter motors. Those ones we can detect when a shooter motor goes out, because we have 2 to compare to. So if we assume that one shooter wheel is spinning and the other one is not, then the shooter wheel that is not spinning is probably incorrect. It is probably broken, or the encoder cables come out. So since we have the 2 motors that are supposed to be doing the exact same thing, we do have the ability to detect when the shooter motor goes out. For the Swerve modules, we've got basically the current angular distance between the module's current position and the goal azimuth angle, and we're running it through our time threshold block, which I can talk more about later if we go through our libraries, our code libraries. But essentially, it's measuring the amount of time that the input value has been above the threshold. So our threshold is 30 degrees, and our input value is the angular error, or angular distance. Basically, we're saying we're counting the amount of time that the azimuth motor has been more than 30 degrees away from its goal. As soon as it gets to within 30 degrees, that timer resets. And what we're saying is that if it's been away from its goal for more than 3 seconds, go ahead and trigger a module fault on those motors. We have also included this option here where we disable the motor failures during autonomous and during, this is during autonomous and also during auto targeting. So we disabled during autonomous because we were getting enough false positives that we were worried it would trigger incorrectly during autonomous, and the autonomous would screw up when it didn't need to. Ideally, we'd make the detections more robust so that we could leave it enabled during autonomous, which would allow us to, oh wait, no, hang on. Maybe we did fix that. I'm sorry, we fixed that. It is actually enabled both for autonomous and for teleoperated. So we were actually checking for module failures during autonomous. Interesting. I thought we were not. As far as I know, we never got a module failure during autonomous. And I'll talk about in a second why that's actually less likely to occur, which I'd forgotten. Okay, interesting. Where we are disabling the module failure detection is when we're in auto targeting. Does anyone have any thoughts on why we would disable the module fault detection when we're auto targeting? What do you think is happening to the Swerve modules when we're auto targeting? Are they moving really fast or really slow? Are they moving a lot or not a whole bunch? Come on, Ethan, guess, or I'll make Mr. Shanafield guess.
Well, they're not moving very much. They're making small adjustments.
So they're making fairly small adjustments. However, they tend to be oscillating pretty rapidly as it tries to maintain. So let me put it this way. If we're auto targeting, the robot is trying to make very small changes to its orientation, to its orientation and its position. However, it's the sign of those changes is changing a lot, right? If it's a little bit off one way, it tries to go back the other way. And if it's a little bit off that way, it tries to go back the other way. And so even though the changes to the robot's location and orientation are small, in order to constantly go one way and then go the other way, the Swerve modules are actually, the azimuth motors are actually moving a lot because they're constantly switching direction in order to make very fine adjustments in all of these different directions. And so what we found was that when we're in auto targeting, even under normal operation, we might never quite hit our goal because the updates are coming so quickly that the modules don't never have time to get to their goal before all of a sudden the goal moves a lot. And so we were getting these triggering these module failures during auto targeting, and we'd get the disabled modules. There are probably cleaner ways to handle this, but you can kind of see how messy the wires are. This was a last-minute fix to try and prevent this from happening in a real match. Maybe even coming at Little Rock, I don't remember. Or maybe even the night before we went to Little Rock. So our solution was basically just don't worry about module failures while we're making these really tight adjustments. Does anyone have any questions on that? Okay. So now I will ask Mr. Shanafield, since he's paying attention. Based on that information, and do you think that incorrect detections of module failures would be more or less likely to happen during autonomous?
Who programmed this section?
I think I did the module faults here.
Then much less likely.
In autonomous?
Yeah.
Why?
And
it has nothing to do with the fact that I programmed it versus someone else.
It has everything to do with the fact that you coded it.
It does not. It actually has to do something with fundamentally how autonomous works.
Well, then I'm going to say there's more false detections.
Okay. Why do you think?
It has nothing to do with you, Luke. Then it's going to be much higher. I'm going higher.
All right. So the answer is that in general, we would expect fewer issues in autonomous. The reason for that is you're right the first time, but not because I programmed it.
The last time I listened to you, Alex.
You should never change your answer.
Yeah, you're right.
So when we're in teleoperated control, it's the driver that is making very tiny adjustments to the joystick, or even if they're trying to hold it steady, right, they're twitching a little bit. And so you have the potential for these very rapid changes in the goal angle for the azimuth modules. In autonomous, this could still happen. However, instead of having a driver trying to hold their hand steady, we have a predefined path that is smoothly transitioning between goal positions and goal angles that's completely controlled by the robot. And so you end up with much smoother transitions between goal azimuth angles, which reduces the likelihood of these really small sort of chatters in the Swerve modules that can cause these false detections. So the smoothness of how autonomous operates prevents some of these problems. I mean, you can kind of see that in that crossfield play that we have. If you look at the videos, the robot it's really smooth how it does the simultaneous rotation and translation. There's nothing special about the Swerve code there. It's not any different than in teleoperated. All the difference comes into how the commands are fed into the Swerve code. And so it's just a little bit easier to be smooth about them when it's the robot doing it versus when the human's trying to make a smooth motion. Are there any questions about that just sort of ramble or off-topic discussion about the smoothness of autonomous commands versus teleoperated ones? Okay.
I have a question. I thought because of pure pursuit, we were always chasing the look-ahead point. So how would it ever get to the goal? Wouldn't we be triggering faults a lot?
Yeah, so that's a good question. So the look-ahead goal is constantly changing. However, you can think about it this way. What we're looking at with the Swerve module failures is the azimuth angle goal. If, say, imagine we're just following a straight line in autonomous. Yes, the position goal is changing, but the azimuth goal, assuming that we don't get too far off the path, is always zero. It's always straight ahead. We'll always have all the Swerve modules pointing straight ahead. And so you can have a constantly changing position goal for the robot in the pure pursuit algorithm and still maintain either fixed azimuth angle goals because you're trying to go in the same direction, or since you're smoothly changing your goal position, like the goal position of pure pursuit, like if you're making a curve, yes, that's changing and your real modules are changing to match that. But again, it's following the smooth path that we've laid out in the path planner with the fillets and with a certain bend radius and everything. And so the Swerve modules are able to sort of slowly get onto target. They aren't trying to make these very rapid changes, and they're not constantly oscillating back and forth about a certain target. Does that make sense, Joanna?
Yeah.
Okay. Are there any other questions about the Azimuth fault detection? Okay. I think we got one more Swerve thing. Oh, just in case anyone's curious, the code that's disabled here was my attempt at doing the the current monitor on each motor to determine whether or not the motor had failed based on the current draw, and it didn't work, so I disabled it. Okay, so the only other one that I want to talk about is alternate rotation centers. So actually, there might be a really good, so let's see if I can find it again. I should have got this before. The Penguineers have a really cool video where they show back in 2012 the robot doing, their Swerve robot doing defensive driving. So let's see. 1712. No. Does anyone remember their team member? It's.
Wasn't it 117?
1717. I think Adam's got it for us. Yeah, 1717. Okay. So let's see, 2012. Yeah. So they actually have a lot of really great Swerve videos. And keep in mind, this was before everything got miniaturized, so their Swerve drive is pretty impressive. Let's see. I think we have to go to their YouTube page because I don't think it was. What is I don't see the video. I don't think it's in the slalom video. It isn't. No, okay, it's the same channel. Anyways, I'll see if I can find it for you guys. I don't know where I saw it. It was one of these videos with their logo and everything at the end. Another example of defensive Swerve driving that's really good is Madtown last year used that extensively in order to get out of tight spots. And essentially what they're doing is, instead of rotating about the center of the robot, they instead rotate about one of their wheel modules. So one of the things that we assumed when we did our Swerve math a couple days ago was that the center of rotation, that the robot was going to rotate about the center of itself. But there's actually nothing in the math that says that has to be true. So if we go back to, I should still have it here. By the way, this PowerPoint is also up on Git. So we assumed that our rotation center was here in the middle of the robot. There's nothing in the math that says we can't put the rotation center here, or here, or somewhere else. And in fact, can anyone think of a situation where we are rotating about something other than the center of the robot now with the robot that we have? Any thoughts for a situation where you've seen the robot spin about a different center point in the center. And it happened all the time. We did every single match. How about auto-targeting? If our target location was out here and we were in auto-targeting, the front of the robot would make sure that it is pointed directly at the target. And as you drove around, you would essentially rotate. You could rotate about that point. Now, part of that is the auto-targeting, and part of that's how the driver actually moves around it. But you can also design a program that would put an arbitrary center of rotation anywhere on the field. So it could be, that's on the field, or something that's all the way out here is on the field. And you could maintain the robot orientation or do whatever you would like while rotating about that center point. So, if we were rotating about this center, the robot would sort of go around in this arc versus, if we were rotating about the center robot, we'd be rotating about, just right about the center. Does that concept of rotating about a different center, a different point in the center of the robot make sense, or is there any questions about that conceptually? Okay. Now there is a generalized solution to this problem where you should be able to pick an XY coordinate relative to the robot to rotate about, and then calculate all of your vector math to set up the wheel angles and speeds so that you'd rotate about it. I messed around with that for a little bit. I think I have the math run out. I never tried to code it. One of the reasons I didn't try to code it was that I don't know how useful that is, and it was fairly complicated. The reason I say I don't know how useful it is I don't know of a scenario where we need to rotate this year about just a completely random point. Now, there are scenarios this year where we might want to rotate about one of our wheel modules. The advantage there being that if you've got a defender robot that's sort of chilling out on your side or over here, you can basically spin around the defender and then drive away. So it's a very clever technique to do that. And the advantage about doing it and just figuring out the solution for just a couple of positions is that you don't have to go through all the math. You can sort of intuit what the orientation of the wheel should be. And so I'm just going to go ahead and duplicate this slide here. And we'll just sort of work through conceptually how it's done. We won't really even need to go into any math for it. We'll just do it conceptually. So, oops. One. Okay. So if we wanted to rotate about module 1, so we want to do something that looks like, let's say, no, that's terrible. Let's say we wanted to do arc. Okay, so here we've got, we want to do this rotation, right? We want to spin about the center of the wheel instead of, I guess, you know, it could be like that. We want to spin about the, I guess that was right. We want to, the center of that arc is lined up there. I wish there was a center mark, but it doesn't look like there is. There we go. So we want to do this sort of rotation of the robot about wheel module number 1. Without thinking about the math side of things, how would we rotate the swerve modules in order to accomplish this? And also, let me go ahead and make this a little bit easier as well. And we're going to make this a square robot as opposed to a rectangular one, since we have a square robot. What do you guys think? So let's start with this wheel module right here. So wheel module number 0, 1, 2, 3. How should this wheel module be oriented? So what if I did the following here? Maybe this will be easier to see. So we've got, oh wow, that's a terrible way to make a circle. It'll take me a second to. So this is terrible. It really doesn't give me the drawing options I need here. Okay. Let's assume that those 2 circles are concentric. I'm going to make a third concentric circle here. Okay, and just assume that this outer circle comes out to this outer corner. It's not letting me resize this the way I want to. So what we're looking at when we're trying to get this robot to rotate about the center is all points on the robot should follow along a circle that is concentric with the rotation point. So if we look out at this wheel here, this corner should be following along this outer circle as the robot rotates. And so, okay, so Adam's looked at this and he says module 3 at 45. So that is what we've got right now. I'll flip the arrow around so that it's sort of pointed this way. Okay, and then module, let's see, module 0 facing forward, like that. Let me there. Okay. And then Adam says module 2 at 90 degrees. So this is what you were thinking about, Adam? Yes. Okay. So yeah, that's completely correct. Let's see. I have this arrow. All these arrows backwards. Both of these arrows are backwards. 1 second. Just if we want to be rotating in this direction. So let me just fix that real quick for us. There we go. Conceptually, does this configuration make sense to people, or are there questions? So mathematically, what we're seeing here is that we can draw, let's see if I can get lines that are actually like not terrible here. We can draw radiuses out from the center of rotation to each one of the modules. And what we're seeing here is that we want each module to be perpendicular to the radius drawn from the center of rotation to that module. Yeah, and so Adam says another way to think about it is you want your wheels to be tangent to the circle. So exactly, so you've got these concentric circles that are coming out to each of your modules, and you want your wheel to be tangent to its concentric circle. If we remember back to the Swerve math, if you recall, what we worked out was that the portion of the radius that matters was the portion of the radius that was perpendicular to the wheel orientation. And so if we want all of the wheel power to go into the rotation, we should align the wheels so that they are fully perpendicular to the radius. So all of the power from each wheel will go into spinning the robot about the circle, and we won't be using any of the power to do a translation or some other crazy type of rotation. Do the wheel orientations make conceptual sense, or are there any questions? Okay, so last thing to think about here is what should the wheel speeds be for all of these wheels? So I'll say this, I want to rotate about this circle as fast as possible. So if I want to rotate about this circle as fast as possible, what should my wheel speed do? With as fast as possible being 1. So 1's the maximum. A motor power of 1 is the maximum value. So what should the motor powers be for each wheel? The module 3 should be at power 1. Okay, so let me write that. So we'll put module 3 at p equals 1. And so we'll say that this size arrow is p equals 1. Okay. What about modules 0 and 2? So Mr. Shanfield or maybe Alex says the power should be a ratio to the other. So Alex, can you say what the ratio should be based on? How we did the magnitudes of the swerve drive.
Like what was it called? We like took like the ratios, like if 1 is the biggest radius, then the other 2 are like that ratio, like the distance.
I see. Okay. So what Alex is saying is these inner wheels are going to need to be spinning at a lower speed. And we have a way to, and that speed difference is going to be the result of the ratio of this diameter out to the further wheel over, or to the distance to the closer wheel. So the reason for this is every point on the robot has to be going at the same omega. It has to be going at the same angular velocity. Otherwise, we'd be ripping the robot apart, right? Different parts of the robot, we're trying to rotate faster or slower than the other parts of the robot. That's not physically possible. Now, if we go all the way back to somewhere, maybe we didn't end up writing it down. Does anyone remember what the relationship was between the angular velocity omega and the tangential velocity coming off the wheel was? How about the velocity coming off the wheel, which I'll just call v for now, is equal to the radius times the angular velocity. So that would be this velocity v on the wheel, which is the one that we're actually setting, is equal to this radius times the angular velocity of the robot. Now, what this says is if, and see, so if this is, I'm going to call this R2, this outer one. Okay. And then actually I'll do this better. I'll call it R3 since we're going to module 3, and V3 is the velocity for module 3. If we look at the power that the velocity for module 2, okay, if omega has to be the same for both modules 3 and module 2, and radius 2 is smaller than radius 3, are these inner wheels going to be going slower or faster than the outer wheels? See Alex mouthing something. I didn't hear any sound. So Alex says slower. So yeah, correct. So these inner wheels are going to be going slower than the outer wheels in order for both of them to have the same angular rotation. Another way you can think about this is the circumference of the inner circle is smaller than the circumference of the outer circle. And so the inner wheels have to drive less distance. Like all the wheels are driving the circumference of their circle. The inner wheels are driving a smaller circumference than the outer wheels. Since they both complete a rotation at the same amount of time, that means that the inner wheels must be going slower than the outer wheels in order to maintain the rotation. And so if we sort of set V3 to be a power equal to 1, then V2 would be equal to R2 divided by R3, and or sorry, times V3, right? So V3 times R2 over R3. So for a square robot, we've got R2 equals the width of the robot, and then R3 equals what width squared plus width squared square root. So the square root of 2 times the width of the robot would be R3. And then, I should also say, and then the module that we're rotating about, we're just going to set that velocity to 0. And if you were to calculate that out, right, R1 equals 0. So if you did the same thing for, if you did the exact same thing for V1, right, we've got R1 equals 0. So you get 0 velocity for the center wheel. Are there any questions at all about either the wheel orientations or the speeds or anything with this idea about rotating about one of the wheel modules? Okay, so essentially what happened was Alex went through and came up with the solutions, the wheel solutions manually for each one of the positions. So 4 solutions for pivoting about module 0, pivoting about module 1, module 2, and module 3. And we just hard-coded those 4 solutions for each one of those possible configurations. And that avoided a lot of more complicated vector math and still got us sort of what we were looking for, which is the ability to pivot about individual modules. So if we go to the code, we can see where we put that in. Let's see. So that is here in this case structure. So under normal situations, we're running the normal swerve math. And then when we're in defensive driving, we are running the swerve defensive driving math. Structurally, it looks pretty, it's pretty simple. Again, we're outputting wheel speeds and wheel angles, but instead of sort of doing all the vector calculations, we just have a different case structure for each one of the different 4 rotation centers. And they're just doing the 4 different combinations to rotate about each one of them. So here's the question. Here's a real challenging question that I don't have an answer to at all. We've got the math done. We've tested it. We know that defensive driving works mathematically. We know that it works on the robot. And we've seen other teams use it effectively, like Madtown last year. Why do you think we have it disabled this year? Go ahead, Alex.
Because we couldn't find a button.
Yeah, I mean, essentially because we couldn't find a button. So if you put yourself in the driver's shoes here, when they're trying to get out of a defensive position, this is probably one of the most stressful times for them. They're probably focused on pretty much everything else other than trying to find a button. And we've got this scenario here where if there's 4 different pivot points, we would theoretically need 4 different buttons, one for each of those. And even if we train the drivers to be really good about remembering where those buttons were, we'd still have a really tough time training the driver to know which one of the buttons to press. So if you imagine a scenario where you've got, let's see, a defensive robot, right, this red one. If the defensive robot's here-ish, you probably want to pivot about wheel module 1. But if the robot's here, then you probably want to pivot about wheel module 3. And then, here, maybe you could pivot about either 0 or 3. Basically, the pivot point that you want to choose, the optimal one, is different depending on where your defender is. And for the driver, I think it would be pretty nearly impossible for them to look down across the length of the field, identify the orientation of their robot, remember which corner is closest to, which corner of their robot is closest to the defender robot, and then pick the correct button to do that rotation, and then actually act on that rotation, and do all of that in enough time that it makes a difference, right? The whole point of the defensive maneuver is to save time. And so it has to be very, very simple. It can't require this much thought in order for the driver to click things. And we never came up with a good solution to this problem. Some of the things that, one of the things that we did play with was trying to set the angle, the pivot point based off of the joysticks to try and come up with some sort of intuitive path forward there. That sort of was sort of unstable. We didn't spend a whole bunch of time on it, and we didn't really get that working reliably. What I'd be interested in is if someone wants to take on the task of emailing Madtown and asking them what their control scheme was for that. How did they have their drivers select, which point to pivot about? I'd be very interested to see if they had buttons or if they were doing something with the joysticks, or maybe it was a sensor, right? You could imagine a scenario where you've got, ultrasonic sensors on all 4 sides of your robot, and it automatically detects whether which side of the robot the defender's on, and then picks that as the pivot point. There's a couple different options, or maybe options we haven't thought about. So it looks like Amelie has been volunteered. But if anyone else other than Amelie would like to also do the email, they can as well. So I think that'd be a good task for someone to reach out to Madtown and see how they did that. Are there any questions about the defensive driving, or any questions at all about Swerve? Because this is the last item on the list for Swerve.
I have a question related to the button mapping. For teams with joysticks, how do they do things that require a button? Do they simply have to sacrifice that? Yeah.
So, Michael, do you mean like sort of the stand-up joysticks, the larger ones, as opposed to the gamepads?
Yes. If I recall, they were mentioned because they basically allow greater degrees with the
Yeah, correct. So all the ones that I've seen teams use do have some buttons on them. The ones that Cheesy Poofs use are very stylish, since the buttons are kind of hidden. But if you look at the part number, they do actually have like 2 or 3 buttons on each one of the joysticks. The joystick that Mars used for a long time when they were doing mechanism drives actually had a ton of buttons on it, I think more than the gamepad even. So that's one solution. It's also true that in general, teams try to push as many of the buttons off onto the manipulator as possible. So they'll try and limit the number of buttons that the driver has to use. And